Hello and welcome back. In this video, I want to discuss kinetic energy, and then I want to talk about the relationship between work and kinetic energy. So kinetic energy is the energy that is associated with the motion of an object, and it's given by this formula right here. So the kinetic energy is 1/2 mass times velocity squared. So just like we did with work, I want to look at the units of kinetic energy. Remember that anytime we have a formula, the units have to be the same on both sides of the equal sign. So we see that the units of kinetic energy have to equal the units of mass times the units of velocity squared. So the units of mass are kilograms, and the units of velocity are meters per second, and we're going to square that. So now what I want to do is I want to take one factor of meters, and I'm going to pull it out. So I'm going to have kilograms, I'm only going to have 1 meters now, per second squared, and I'll take that whole thing and multiply it by meters. So I still have the same units, I've just factored out 1 meter. But when I do this, these numbers now that are in this parentheses, we can see this is a kilogram meter per second squared, and that's what we call a Newton. So we see the units of kinetic energy are newtons times meters. And we talked about this before in the previous video. This is the same units as the units for work. So kinetic energy has units of joules, which are the same units as the units for work. Now, when we talked about work, I said the force that tends to, by itself, cause an object to speed up is positive work. And the work that tends to slow an object down is negative work. Now, the WorkEnergy Theorem is a theorem that allows us to describe the actual change that will happen to an object when work is being done. So in a more precise terms, the total work that is done by all of the forces acting on an object is equal to the change in the kinetic energy. So again, this means that if the work is positive, it's going to increase my kinetic energy, so it'll tend to speed the object up. If the work is negative, the change in the kinetic energy will be negative, so it'll tend to slow the object down. Now, one thing I want to point out is it turns out the WorkEnergy Theorem is very closely related to one of our kinematic equations. So the WorkEnergy Theorem says the net work that's done on the object is equal to the change in the kinetic energy. So the net work, the formula for this is it's the force that is parallel to the displacement times the displacement, and this has to equal the change in the kinetic energy. So the change in the kinetic energy, or let me just leave it as delta KE for now. So if I apply Newton's second law, the sum of the forces on an object is equal to mass times acceleration. So the sum of the forces that are in this direction that's parallel to the displacement will equal mass times the component of my acceleration that's parallel to the displacement. Right? Just like the sum of the forces in the x direction gives me mass times the component of my acceleration that's in the x direction. So for work, we multiply that by the displacement, and this equals the change in the kinetic energy. So the change in kinetic energy, that's 1/2 mv final squared minus 1/2 mv initial squared. And I can factor out this 1/2 m because it's in both terms. Now, one thing I want to point out, let me just kind of put this over here. A lot of times I'll see students write this. They'll say the change in kinetic energy is equal to 1/2 m times the change in the velocity squared. This is not correct, okay? This is, so if we wrote this out, that means 1/2 m v final minus v initial squared. And if I FOIL this, if I multiply this all out, that's 1/2 m v final squared plus v initial squared minus 2v final v initial. That's not the right formula. Obviously, that's not the same thing as what I have written down here. So do not do this, right? So it's the change in kinetic energy is not 1/2 m delta v squared, okay? It's 1/2 m v final squared minus 1/2 m v initial squared. Now, as I've written this here, we can see that we have mass on both sides of the equation, so I can cancel this out. And now if I multiply this whole thing by 2, so I'm going to multiply both sides by 2, I get 2 acceleration that's parallel to displacement times displacement is equal to v final squared minus v initial squared. So this equation we have right here is very, very similar to another kinematic equation we have. This v final squared is equal to v initial squared plus 2a delta x. And actually I should say this is the x component of my final velocity and the x component of my initial velocity. There's a couple things to note though. There are some differences between these two formulas. The work-energy theorem tells me the change in the magnitude of my velocity. So it tells me the change in the speed of the object. And it says that the change in the speed only depends on the component of the acceleration that's parallel to my displacement. Whereas this kinematic formula we have here, we apply this separately to the x direction and the y direction. So this will tell me the x component of my velocity, and I could solve it again and find the y component of my velocity. Okay? And it tells me the x component of my velocity depends on my acceleration in the x direction and my displacement in the x direction. So let's go ahead and look at a couple of examples. The first example says, when a jet is launched from an aircraft carrier, a spring-powered catapult is used in combination with the jet's engines to reach the velocity necessary to take off. Both of the forces are parallel to the carrier's runway. When taking off from rest, the jet moves 87 meters down the runway and takes off with a kinetic energy of 4.5 times 10 to the 7 joules. During this time, the engine produces a force of 2.3 times 10 to the 5th newtons. Ignoring friction, how much work is done by the catapult when the plane takes off? So one bit of information we're given here is we're told that the jet starts out from rest. So what this means is the initial velocity is 0 meters per second. And because kinetic energy is 1/2 mv squared, this means the initial kinetic energy is 0 joules. So let me go ahead and just show a little picture of what's going on here. So we have this aircraft carrier, and on the aircraft carrier there's this jet. And there are two forces that are acting on the jet that cause it to speed up. There's the force that the engine exerts on the jet, and there's this force that the catapult is exerting on the jet. And the jet's going to be moving to the right. Okay, so it's going to be moving in the same direction as these forces. And we're told the distance that the jet moves down the runway is 87 meters. We're also told the force that the engine exerts on the jet is 2.3 times 10 to the 5th newtons. We're told that the final kinetic energy of the jet is 4.5 times 10 to the 7 joules. And we're also told that the initial kinetic energy, because the plane starts from rest, is 0 joules. And what we're asked to do is calculate the work that's done by the catapult. So the work-energy theorem tells us that the total work that's done by all of the forces is equal to the change in the kinetic energy. So the total work that's done by all the forces is the work that's done by the catapult plus the work that's done by the engine. And this has to equal the change in the kinetic energy. So if I solve for the work done by the catapult, I see this as the change in the kinetic energy, which is the final kinetic energy minus the initial kinetic energy. And because my initial kinetic energy is 0, I can just write this as the final kinetic energy minus, if I'm solving for the work done by the catapult, I'll subtract this off, so minus the work that's done by the engine. And the work that's done by the engine, we have to use the formula for work to calculate this because we weren't given the work that's done by the engine, but we're told the force that's exerted by the engine is 2.3 times 10 to the 5th newtons, and we're told the plane's going to move 87 meters down the runway. So remember, work is force times displacement, and because they point in the same direction, cosine of 0 is 1, so we don't have to worry about that. So the work that's done by the engine is the force exerted by the engine times the displacement of the jet. So if I plug all these numbers into the calculator now, if I take the kinetic energy and subtract force times displacement, I see that the work that's done by the catapult is going to be equal to 2.50 times 10 to the 7 joules. So that's the work that's done by the catapult. So we can see that, almost half of the work is done by the catapult, and about half of the work is done by the engines. In fact, just a little bit more than half of the work is being done by this catapult that slingshots the jet off of the runway. So I want to look at one more example, and this is a pretty complicated example, or a more difficult example. So the example says, a skier starts from rest and begins coasting down a 25-degree slope. The coefficient of friction between the skier and the snow is 0.25. The skier coasts 10.4 meters before jumping off of the edge of a 3.5 meter cliff. How fast is she moving when she lands? So the first thing I want to point out about this is that we should break this motion up into two parts. So during the first part, she's coasting down a hill that's 25 degrees. So there's this part of the motion, and then after this she's going to jump off a cliff. And when she jumps off the cliff, she's just going to fall free fall motion. So it'll be projectile motion. So obviously these two motions are very difficult. During this first part, very different. During the first part, she's forced to move along this surface. And during the second part, she's now in free fall. So because these two motions are so different, we're going to want to break this up into two different parts and calculate the work that's done by gravity and friction during the first part, and then the work that's done by gravity during the second part. Once we calculate the total work that's done by all of these things, we can use the fact that the total work that's done by all of the forces during part 1 and part 2 will be equal to the change in the kinetic energy. And then we can use this to calculate how fast she's moving. So I think I'm going to need a whole lot of space for this, so maybe I'll use one note for this. Okay, so here's the problem we're looking at. We're told that during the first part of the motion, skier is moving down an incline that is at 25 degrees, and the coefficient of friction is 0.25. We're also told that she's going to ski 10.4 meters down this incline. So I'll call this delta R1 for the displacement during the first part of the motion. And we're told during the second part of the motion, so when she comes down and she jumps off of this cliff here, so this is not really her displacement during the second part of the motion, but we're given the y component, or the vertical component of her displacement during the second part, and that's going to be 3.5 meters. So we don't really know her displacement, right? Because she's going to come down here and then she's going to jump and she's going to land somewhere. We don't know how far in this horizontal direction she's going to travel, but we know that she's going to travel down by 3.5 meters when she jumps off of this little jump here. So let's go ahead and look at the first part of this. So during the first part, work is being done by two forces. There's the force due to gravity, and then there's the force that's done by friction. So let me go ahead and draw a little free body diagram here. So we've got this person here. So there are two forces that are doing work. There's the force that's done by gravity and the force that's done by friction. So I'm not used to using this. The force due to gravity points down like this, and the frictional force is going to point up the ramp like this. So the work that's done by gravity, right? One way we could calculate this is the force due to gravity times her displacement when she's going down the ramp, times cosine of the angle between these two things. So if we think about this, we're told that she's going down a 25-degree ramp. So this angle right here is 25 degrees. So the angle between her displacement and the force due to gravity, so if she's going down the ramp, her displacement looks like this, right? She's going down the ramp. So this is delta R. So we can see by looking at this, the angle between the force due to gravity and delta R, that's this angle up here in the triangle. So if this angle down here is 25 degrees, then this angle up here, this is the angle between force and displacement, this is going to be 90 degrees minus 25, or in other words, it's going to be 65 degrees. So the work that's done by gravity is the gravitational force times displacement times cosine of 65 degrees. So that's mg delta R1 cosine of 65 degrees. Now, the work that's done by friction is going to be a little bit easier, right? Because the frictional force always opposes the displacement. So the displacement's down the ramp, the frictional force is up the ramp. So the angle between those two things is 180 degrees. And remember, cosine of 180 degrees is -1. Right? It's going to be a negative work because the work is opposing the motion. So we see that the work that's done by the frictional force is just minus the frictional force times the displacement during the first part of the motion. So the frictional force, remember this is minus mu times the normal force. So the normal force, it's going to cancel the gravitational force that points downwards against the slope, perpendicular to the slope, right? So this is the force due to gravity times cosine of the angle of the ramp. So this is cosine of 25 degrees. So this whole thing here is just the frictional force, right? It's mu mg cosine of 25 degrees. And we're going to multiply this by the displacement. So the total work that's done during part 1 is the work that's done by gravity plus the work that's done by friction. So this is mg delta r cosine of 65 degrees minus mu mg delta r1 cosine of 25 degrees. So that's the total work that's done during this first part of the motion here, when she's going down the ramp. During the second part of the motion, she's going to now jump off of this jump here. So during the second part of the motion, if we think about this, right, her motion is very complicated, right? It's not like she's, moving in a straight line like she does when she's going down the ramp. Here, the direction she's traveling is always going to be changing. So figuring out the component of the force that's parallel to that direction she's traveling is going to be, extremely complicated. And in fact, we would have to use an integral to calculate it because the component of the force that's parallel to the displacement is always going to be changing because the direction of her motion is always going to be changing. But remember, there's a lot of different ways we could calculate the work. And an easy way to calculate the work in this case is it's going to be equal to the force due to gravity times the component of her displacement that is parallel to the gravitational force. Right? So if we think about her displacement during the second part, there's a displacement that goes down and a displacement that goes over. Right? This is her displacement during the second part right here. This is delta R2. And the part of this that's parallel to the gravitational force is this vertical displacement. So this is exactly like the one example we did when we were first talking about work. Right? There was this example of a person standing on the edge of the cliff. We asked, what was the work done by gravity? If the student throws the rock vertically up into the air or vertically down off of the cliff or throws it horizontally. And we found that the work that was done is the same no matter what the path is. So that's the same thing here. It doesn't even really matter what the path of this skier is as she goes off of this jump. The only thing that matters is this vertical displacement. Right? So the work that's done by gravity is just the gravitational force times that vertical displacement. So during the second part of the motion, the work that's done during the second part of the motion is just going to be equal to the gravitational force times displacement in this y direction. And we were told that that's a 3.5 meter cliff, so that's how far she's going to fall in the vertical direction. So it's just going to be mg times delta r 2 comma y. So that means the y component, or the vertical component, of her displacement during the second part. So the work-energy theorem says that the total work that's done by all of the forces during both of these parts is equal to the change in the kinetic energy. So the total work equals change in kinetic energy. So the total work that's done by all of these forces during all parts of the motion is, so let me simplify things a little here. So we have mgr is in both of these two things. Right? So we have mg delta r1 times cosine of 65 degrees minus mu cosine of 25 degrees. So I just factored out this mgr1 because it's in both parts. Plus the work that's done during the second part of the motion, that's mg delta r2 in the y direction, and that's going to equal the change in the kinetic energy. Now, we're told that initially she starts out at rest. So the change in kinetic energy is just the final kinetic energy, which is 1/2 mv final squared. So we see everything depends on mass, so that cancels out. And we see that the final velocity squared is just going to be equal to 2g delta r1 cosine of 65 degrees minus mu cosine of 25 degrees plus g delta r2 in the y direction. And finally, if I'm solving for the final velocity, I can just square root both sides. And if I plug all this into a calculator, I see that the final velocity is equal to 10.4 meters per second. So at this point, I think I'd like to end this video, and in the next video, I'm going to talk about conservation of energy.